take a signal, amplify it, send it to the antenna. Basically what we're doing right? The question is, how does this affect our amplifier? Okay, if we go back over here, I'm going to draw my small signal one more time. Let's say we now connect some load resistance, RL. Okay. What happens here? Okay. Still have V naught. Well, RC and RL are now in parallel, right? When you put two resistances in parallel, the equivalent resistance decreases, right? So we go back from before, the equation I wrote. It's not going to be RC parallel RL over whatever is in the bottom here, right? This doesn't change. But our numerator is now RC parallel RL. That's always going to be smaller than RC, right? So what that means is our gain now decreases because we've attached something. We don't want that. We want to attach any resistance we want to it and have the gain be ideally the same. That's an issue. We want to take away our dependence on our load. Whatever our collector sees, we want to take the dependence away. So there's one main way of doing this. We go back over here. We can see something kind of interesting is we have, I'm going to erase this. We have, say, an amplifier stage. Okay? Just like we did over here. And we have, say, our antenna. Okay? What we want to ideally do is say, hey, let's look this way, right? Let's make this RL kind of infinity. RL is infinity. Something in parallel with infinity is just that RC, right? That makes sense? So we make it such that our RL looks extremely large. Our gain is still negative GM/RC. That's the idea. So we want to see some sort of infinite resistance looking this way. But from the antenna perspective, we want to receive a signal and transmit it. So we want, ideally, to see whatever signal is over here unimpeded. So we want to see 0 ohms going this way. So like, okay, how does that work? How do we, have one being infinity, one being 0? In reality, of course, we can't have infinity, we can't have 0. We can have very large values and very small values of resistance. So this is when we get to something we call a buffer, because a buffer separates our amplifying stage from our output. It buffs them, in a way, hence the name buffer, right? So a buffer, funnily enough, uses a BJT. Same thing we've been using this whole time. Okay? And this is called a common collector. We're running a bit short on time. There's one thing I'd like to talk about after this buffer that I'll mention about the physics. So we have something looks like this now. And we take our output here instead. Kind of weird. So we're now taking our output at our emitter instead of our collector. Slightly different, okay? And we'll see why. So, same RE, okay? And just like before, we apply our small signal model. Input goes down into R pi, goes over here. Still have our degeneration resistance, RE. Dependent current source. And that's it, right? GM, V pi, V naught, right? So, well, what kind of happens here? we can go through dual the KCL, dual the KVL, and we'll see that V naught, VI, call our A V, right? This is going to be RE over 1 over GM plus RE. Right? So what's happening here is we know this is always going to be less than 1. Okay? For very large RE, GM, 1 over GM doesn't compare. Say 1 over GM, let's say it was around 26, right? RE, let's make it like 1,000. So 1,000 over 1,026, pretty close to 1. May as well be. We have a gain of 1. Okay, it's kind of weird, not amplifying. What's the point of this, right? So if we look this way, if we look at the impedance looking into the base, okay, we're going to have a very large impedance, right? That's good. If we look at our impedance from our output, R out, we get a relatively small one. Again, satisfies this. So I'll write down a few more equations that kind of describe the R in and R out, and we will kind of see their relative magnitude. Okay. So let's see. Okay. So the R in for our buffer circuit here is going to be R pi plus beta plus 1 RE. Beta is around 100. R pi we said is already around like 2K. So 2K plus 100 times, I don't know, let's say 100. Pretty large value. Okay, this is great. And this is typically always going to be a very large value. Okay, so that's great. This is going to be very large if we make RE very large. If we make RE very large, this is going to give you gain of 1. So this means we can shove this thing between our amplifier and our antenna, not have any decrease in our signal. This is 1. And, hey, we don't load our amplifier stage from before. So we'll see a very large resistance looking in. That's going to be so large that this is going to be the only thing we care about for our gain. Pretty good. Okay? So that's something we employ all the time in rap. These two know about it. And if we do the hardware track, we're going to be putting all of that together to one block. So overall, what we kind of covered is we have an amplifier stage. Take the output, okay, feed it into our buffer, okay. Take this output, and now attach it to an antenna, okay. So let's say this has a gain of 10. Let's say this has a gain of 1. Ideally, this means we apply a certain signal here, call it VI. It's all small signal, by the way. We're going to see 10 VI here. In real life, we can never get this to be 1. It's going to be maybe around 1/2, 1/3. Okay? So on paper, that's kind of bad, but it still gives us the good property of isolating our amplifier from our load. So this gain decreases, 1/2, 1/3. But we can still play with this gain. We can have several amplifier stages before this to counteract this. And we'll talk a bit more about that, perhaps at some later point. So, just to recap, what we've done is we've talked about diodes, talked about how these BJTs work, and then how to use them, how to exploit their current multiplying properties to give us gain. One thing I'll bring up that I've not mentioned yet has to do with our transistor model and something that is always going to limit our gain, you know? From our prior equation, negative GM RC, at first glance, if you make RC infinity, you get infinite gain. But like I said before, physically you can't do that. What's the reason for it? So if we draw our small signal model, and let's say we do not have any collector resistance, something that looks like this. We will have some resistance here, intrinsically, to our device. So, hey, no more RC, but this is always going to be here, okay? What this does is it's our intrinsic gain, it's our intrinsic gain. So now even if we have an RC, right, we attach our RC here. Our gain, negative GM RC, number 4, parallel with this resistance. So if this R naught is infinity, this is an open circuit. It's the same equation as before. It's never infinity in real life. It's again somewhere in the thousands range, but you can't ignore it. And the reason this comes around is from before. When we look at our curves, we have SC versus VCE. Remember how before it was kind of going something like this, right, generally? And it's flat over here. We want it to be flat. That means we've now isolated the dependence of our current on VCE. This can go all over. Current doesn't change. That's perfect. In reality, what kind of happens, it goes up a bit. So then it looks like this. Okay? Still very linear dependence here. And because linear, extract the slope. Okay? The slope is what we call R naught. Okay? What this is basically saying is, in real life, you still have the collector having an effect on your current. And it follows this relationship, this slope here. Okay? That's where this R naught comes from. Okay? What exactly is this R naught if we extrapolate this all the way back here? It's going to intersect at something we call negative VA, or the early voltage. Okay? So what R naught is it's a way of quantifying this early voltage in a way that we can use it in our small signal model. Okay? So what R naught is it's going to be VA for IC. Okay? It's the slope here, the inverse. And this is something that persists throughout all our models. So if we go back at our common emitter amplifier, this is now the equation for it. We go back and look for common emitter amplifier with degeneration resistance. AV is now negative GM, RC parallel R naught, or 1 plus 1 over R pi plus GM RE. So this lowers it lowers our gain. And it's something we can never avoid. It's something we design around. It places an upper limit on the gain we can have. So if we want to say a gain of 30, but the max limit we can get from our amplifier is 10, we just have to string together multiple amplifiers. And a lot of the time, hey, you can't maybe use exactly 3. Maybe you need 4 because of just more non-idealities, because of loading. But generally speaking, negative GM RO is the max gain we can get from an amplifier. It's pretty cool. Typically, you'll have gains be around 20 to 30 if you're really lucky. In practice, in rap, we've got mainly around 10 to 20 or so. But yeah, that's pretty much something that we can never avoid.
What's stopping us from infinitely cascading amplifiers?
Yeah. So when we cascade amplifiers, kind of leads me to Eli's earlier question. Amplifiers here have a certain input resistance still, that's going to load our prior stages. Changes our gain a bit, so we have to work with certain things. This means if we have a bunch of amplifiers, we have to look at this last amplifier, figure out what the resistance looking into it is, and then kind of backtrack. More complicated, it's a 115A B question. How do we string them together? As for your other questions, hey, if we have a bunch of amplifiers, what's stopping us? Well, eventually at some point, we start with the idea of small signal, right? We apply a small signal and it gets amplified, all right? That's great. If we keep stringing together amplifiers, we'll have a relatively large signal here. Still small enough, it keeps us in this small signal regime. But it'll then get replicated at V0 with an even larger magnitude. And V0 can't go too high or too low. This is VDD, right? That's our collector voltage, okay? VCE has to be at least 0.3 typically, okay? VDD is around 5. This means if this drop here across RC is larger than that, larger than 4.7, your transistor's turning off. In fact, it'll turn off before. But this means that if this is large, it gets amplified. V0's going to be swinging super high and low. And if we were to plot it, that's going to be pretty large. You know, maybe earlier when we talked about using an amplifier initially, V0 is still maybe, I don't know, in the tenths of a volt or something like that. But now, if V0's having swings like, you know, 2 volts, -2 volts, you know, stuff like that, that's quite large. It can easily push our transistor out of our bias conditions. And that just ruins the whole amplifier then. Because our gain, our GM, is set by whatever current's going through it. If this turns off, current is 0, GM 0. You just mess up the whole system. So that's something we have to keep an eye out on, is when can we stop amplifying? Because at some point this happens, it clips. And I mentioned, and something we'll talk about later, is if this goes too high, our signal is now going to look like this. It gets kind of cut off. It's more like a square wave now than just one frequency. So now we get harmonics popping in. Odd harmonics, to be particular. So that's just a bit more extra information. But generally, yeah, you can string together amplifiers. What's up?
So you discussed that we have a gain of GM times RC, change of RC, we just have one resistor. You throw on a second resistor for stability over temperature. Is there a way that we can have stability over temperature while still maintaining that gain of maybe GM times RC?
You can also bias your base with different resistors to set this voltage. For example, VDD. Something I may talk about next lecture is you can bias your base now. So this holds the voltage for the voltage divider principle. This doesn't move around as much. This doesn't move around as much. So overall, won't shift as much as temperature. Is that kind of what you're getting at, or?
What if you put a capacitor in parallel with the emitter resistor?
Yes, that's the bypass capacitor. Yeah. So going back, I erased it. Okay, whatever. Another thing that we do, we operate certain frequencies. 1 megahertz at the microcontroller. Then we're going to go to 5 megahertz, 27. We operate certain frequencies, is the point. And if we see certain frequency here, okay, we want some way that at our frequency, we are not affected by this resistor here. So what we do is we, this capacitor, parallel with some capacitance value. And what this does, let's just say for sake of convenience that at a certain frequency, this presents a certain impedance, right? This capacitor, right? 1 over J omega C, right? Let's say at 1 megahertz, we apply a signal here, okay? This 1 megahertz signal is going to see in our small signal model this resistor in parallel with this impedance here. This impedance is designed to be very large, or like small rather, right? If this is going to be very small at this frequency, what happens is this signal, if it goes to our small signal model, is going to see a short right here. Okay? This is very small. This impedance. So this impedance is very small. A signal coming through is going to go all the way over here and go down this path. Okay? So if you make this super small, this impedance in parallel with this resistor, this is going to be practically 0, right? So this means that we no longer see RE in our small signal model because it has this other path for it to go through. So in terms of our gain now, this is now a way for us to say, hey, our gain can still be negative GM, RC parallel, R naught. We just put certain capacitance here that allows signals to go down this path. They're not going to see this resistance anymore. Totally gets bypassed. It's not a bypass cap. So we don't see the denominator of 1 plus RE 1 over R pi plus GM. This just goes to 0, effectively. Because this RE is the impedance looking this way. These two in parallel, this is smaller, practically around 0. You see 0 resistance. This RE is 0. 1 plus 0 is 1. It's a general idea. Eli, what's up?
So is there a reason we would prefer the bypass capacitor method to like the
Well,
transistor method?
We use this all the time.
Okay.
Again, it's not perfect. You can never have 0 impedance because you're limited by this equation here. But we can design for it to maybe be a 1/10 of RE. There's a 1/10 of RE. That means it's going to be a lot smaller. It's going to take up most of the signal path, which means this kind of more or less holds. Yeah.
Okay.
Wouldn't adding an AC short there, the bypass capacitor, wouldn't it kind of cancel out the effects that you get, limiting temperature fluctuations?
It still has it there, because for your DC bias, right? That's what you care about. Temperature affecting your DC bias. Your DC bias is still maintained by this impedance here. So this becomes open, right? Your DC, you still see RE here, right? Which means this is still kind of, this voltage is still kind of held in a way, so you can't swing around it as much. So the idea is, it still all looks the same for DC. Your capacitor just allows the frequency of interest to go past unimpeded, relatively unimpeded. Yeah. Any other questions on that? I know it's a bit tricky, but this capacitor is something we use all the time. Buffers in between amplifiers and subsequent stages, we use all the time. It's something you'll see in your modules as well, as you go through and do simulations. Design an amplifier that has this game, design a buffer that does this, that type of thing. And of course, all of these things will be posted as well. So you have all the equations there, ready to go. It's just a matter of getting LT Spice up and running. Yeah. Any other questions?